Okay, thank you very much for the invitation. And this is my second time at the National University of Singapore. Last time is 4 years ago. I gave a talk on the elliptic genus. This time I give another talk on my another research direction in the quantum topology. So my title is the recent progress of various volume conjectures for links as well as solid manifolds. So this is some joint work of several different research groups. The theme of my talk is intertwining of mathematics and physics. This is the area of quantum topology is heavily influenced by the ideas from physics. So we know the volume conjectures for Colored-Jones polynomial, and also the idea from the large N duality, the Chen-Summers gauge theory, the duality between Chen-Summers gauge theory and the open topological string theory. And currently, so we find some new volume conjectures for trial virial invariants and Recursion trial invariants. Those invariants haven't been discovered for such volume conjectures at their original root of unity. Because at the original root of unity, considered by Edward Witten, it is only polynomial growth. And then now we consider the root of unity q squared instead of q. So then we discover some, it should be exponentially large, and the growth rate is proportional to the hyperbolic volume of the solid manifold. And then, because it is, many people believe there should be some non-unitary physics theory corresponding to this Recursion trial invariance or trial virial invariance evaluated at q squared. So it should be a non-unitary theory, but nobody knows what this kind of theory should be. And so we think it can maybe indicate some new physics. So I quickly review the setup of the quantum topology. So this is a knot, is a simply closed curve embedded in R3. Then the link is just several copies of knot. And the important thing is to distinguish the different knots and to find some invariants to distinguish those knots. And this is just some basic examples of knots. So this is the simplest is N knot. This is a trefoil knot. Is the simplest non-trivial knot. And this is the simplest hyperbolic knot. It is called the figure 8 knot. And this is the Hopf link. Is the simplest links. And so mathematicians want to find finer and finer invariants to distinguish those different knots. And those kind of invariants has been connected to different branch of mathematics and physics. So in this talk, I first quickly review the history of the early development. So here I call it early development because those invariants can be defined by by the scan relations. So scan relations is some combinatorial method to define. So here basically, so this is the small neighborhood. So L plus means only inside this small neighborhood, it is a positive crossing. And L minus means inside this small neighborhood is a negative crossing. The positive crossing, negative crossing, and the smoothing. So that means each time you apply this scan relation, then you can reduce the number of the crossing by 1. So if you have finite number of crossings, then if after finite steps, you can calculate the invariance. So this is the scan relation for the Humphrey PT polynomials. And this is the initial condition, is 1. Okay, so this is the scan relation for this one, for Humphrey PT polynomial. So actually, Alexander polynomial and the Jones polynomial was defined by other method. But the generalization is the Hanfly-Pity polynomial. So in the Hanfly-Pity polynomial, if you take a t equals q squared, you get a Jones polynomial. If you take a t equals 1, that means q to the 0, you got the Alexander polynomial. Okay, then revolution always happens when physics enters into the picture. So here, I treated this as the early development because you're just using some simple combinatorial question. Yes. T equals 1, then this is the scalar relation. Yeah. If we t equals q, there's nothing. You can get nothing. T equals q squared, you get a Jones polynomial. T equals 1, you get the Alexander polynomial. Alexander-Conway polynomial, actually, it's called. Okay, then we enter the modern development. So in 1988, the Triumph first recognized the Hanfly-Pity polynomial as the invariance associated with the fundamental representation of the quantum groups by setting the q to the n equals t. Then, this is Witten's famous paper in 1989. So Witten interpreted the Jones polynomial by introducing Chen-Simons gauge theory and predicted the existence of the new invariants of knots and links, as well as the three manifolds at the roots of unity. So I want to emphasize here the roots of unity is q equals q1. So actually, in his original paper, this is physics notation. This is math notation. So I just to emphasize some notation here. Physics notation, what is q1? So they want to write e to the 2 pi I over r. And in math, we use this kind of notation, e to the pi I over r. And q2 is e to the 4 pi I over r. 2 pi I over r. Here r should be odd, the same. R should be odd. So this is because in Witten's original paper, he write q1 is 2 pi I over r, but in our notation is pi I over r. Anyway, so this is just slightly different in notations. And Witten's definition is not rigorous, and because it's involved the integration over the infinite dimensional space. And then 1990, Recursion and Triumph, they use the representation theory of quantum groups, not only construct new invariants of those knots and links and the three manifold predicted by Witten, but also at the other roots of unity. So here I want to emphasize those roots of unity because it can become quite significant in the second part of my talk. So we find the volume conjecture at the other root of unity, except at the original root of unity. So that means Recursion Triumph, they construct those invariants at Q1, and Q3, Q5, Q7, all the order numbers. And then 1992, Triumph Vero, they use some called a shadow model and use the quantum 60 symbol. So quantum 60 symbol was originally defined by Krylov-Reshetikhin. And they used the quantum 60 symbol as the building blocks to construct invariants of three manifold at the roots of unity Q equals QS. I and S are co-prime. So actually, Triumph Vero, they defined those invariants at Q1, Q2, Q3, any root of unity. So the Triumph Vero theory has a very tight connection to the 2+1 dimensional quantum gravity. Because if you know some quantum 60 symbol, you also know quantum 60 symbol has a very tight connection with the quantum gravity. It's also called the Pozzano-Reggi model. So here is the brief history of the quantum groups. The quantum groups was due to the Leningrad school led by Faddeev and also Coolidge. And I think Faddeev is Reshetikhin's first advisor and Coolidge is the second advisor, but they both passed away just recently, 1 or 2 years ago. They gave the first example of the quantum groups. And then Junfeld and Jingbo in 1986, they formalized the above idea to the general definition of quantum groups. Some further development Giovanni Feld developed the elliptic quantum groups. This is history of the quantum groups. So previously, I think in your talk, so you used Giovanni Feld's some construction to study the four-dimensional quantum Chern-Simons theory. So this is also some basic setups. So basically, you have a knot in the three-dimensional space. Then you put a light to project to the two-dimensional wall. So two-dimensional wall, then you have a lot of crossings. It's positive crossing, negative crossings on the wall. Then you write down from upper part to bottom part. You write down those endomorphism. And then you associate each crossings to an R matrix. The R matrix is a solution of the Yang-Baxter equation. So for positive crossing, you associate it to R VV, and for negative crossing, you associate it to the R VV inverse. And in such a way, you get an endomorphism. Then you want to take the trace. So we don't take the normal trace, we take the quantum trace. So what's the difference between the normal trace and the quantum trace? So the normal trace is like this. The normal trace, you have A11 plus A22 plus A33, right? Until ANN. The quantum trace, the Q trace, so for different quantum groups, that's for example, so it's like you have a weighted trace. You have such kind of weighted trace. So this is called the quantum trace. So after you take the quantum trace, then you got the quantum group invariance. This quantum group invariance is independent of choice of such projection to the two-dimensional wall. So independent of choice. So you can prove that is well-defined. So because of the centralized algebra of the quantum universal enveloping algebra, the quantum group, it's a Hecke algebra. And if Q is not a root of unity, the Hecke algebra is isomorphic to the symmetrical group. So then we can use the representation theory of the symmetrical group to study the representation theory of the quantum groups. So here is some basic notations for the representation theory of the symmetrical groups. For example, so we have such a Yang tableau. So total have 11 boxes. So you can see here 4 plus 3 plus 3 plus 1 is 11. So 11 boxes. And L mu means you have 4 rows. You have 4 rows. So here is this row is first row, mu1 is 4, mu2, mu3 is 3, mu4 is 1. And here Z mu is the order of the conjugacy class. So 3 appear 2 times. So here you have 2 factorial. And here this is an example for the Yang diagram. So just for the simplest knot, for the N knot, we have to calculate this quantum invariance for this N knot. So actually, so it looks like this one. So this is for previous example, the mu1 is 4, mu2 is 3, mu3 is 3, mu4 is 1. So totally you have L mu equals 4 for the previous example, for this example. And the Z mu is the order of conjugacy class, and the C mu is the conjugacy class. Chi A is the irreducible character associated to this Yang tableau. And WA is called the quantum dimension of the corresponding representation space VA, and it's denoted by the quantum dimension. And for each Yang diagram, there exists such 2 variable quantum invariance equal to this 1 variable quantum invariance. And this 2 variable quantum invariance we call the colored Hanfly PT invariant, not the colored Hanfly PT polynomial, because it's not a polynomial yet. It's quantum colored Hanfly PT invariant. Then here we give a summary. This is the building of the quantum invariance. So I missed some important part is the Alexander polynomial, because Alexander polynomial is a little bit complicated. So it's just studied recently. So it's a SL Lie superalgebra. It's corresponding to this SL 1/1. So I didn't list it in this building. So the first floor of this building is the non-categorification. The second floor is the categorification in the sense of Hovanov and Hovanov-Rozansky. This is categorification, and several people by my academic brother as Ben Webster. Finally, this program is finished by Ben Webster. So here, the fundamental representation and UKSL2, you get a Jones polynomial. Fundamental representation of UKSLN, you get a Humphrey polynomial. Then this is the type B, type C, type D, and the algebra all give you the Kaufman. And here, any irreducible representation, you get a colored Jones, colored Humphrey, colored Kaufman. So this is the first floor. And not we only have the second floor or third floor, maybe. We also have some secret internal to other branch of mathematics. So here's several secret internal. The first one is probably the most important one. So it's so-called the original volume conjecture. It is proposed by Kashif, Murakami. By Kashif in 1997 and Murakami in 2001. So this is the secret internal to the low-dimensional topology, hyperbolic geometry. The hyperbolic geometry, the modern hyperbolic geometry is established by William Thurston. And here is some colored Humphrey has a secret internal to the open Gromov-Witten theory. It is so-called the LMOV conjecture, Labastida-Marino-Uguri-Waffa conjecture. It is proved by Kifeng Liu and Pan Pen about 10 years ago. And this is part of my PhD thesis, is orthogonal LMOV conjecture. It's proposed by Lin Chen and me, and we just proved several special cases, not all. This part is some hints to get one side of the generalization of the volume conjectures. But today I don't have time, so I will quickly I don't have time for the LMOV conjectures, but I can give you some just physics motivation for the LMOV conjecture. I don't want to introduce the mathematical part. This I don't have time today. So the LMOV conjecture come from a series of work done by four physicists, Labastida, Marino, Uguri, and Waffa, inspired by the large N duality, which is pioneered by a seminal work of de Hooft in 1974. The history of the original large N duality is also from Witten, 1992. He recognized the Chen-Simons gauge theory on S3 is equivalent to the open topological string theory on the deformed conifold T star S3. Deformed conifold is just a cotangent bundle of S3. And in 1998, Waffa, they identified the open topological string theory on the deformed conifold is equivalent to the closed topological string theory on the resolved conifold XS3. This resolved conifold is Calabi-Yau threefolds. And so from these two, you can assert the following. The Chen-Simons gauge theory on S3 is equivalent to the closed topological string theory on XS3. This is computed by Faber Panda by localization techniques. So this is actually, we call it the closed large N duality. Then we can also insert a link here in S3. Then there's a corresponding special Lagrangian corresponding to this link in S3 inside this XS3, because XS3 is a three-dimensional complex manifold. It's a six-dimensional real manifold. And a special Lagrangian corresponding to that is a three-dimensional real manifold. And if here you inserted the N0, then the special Lagrangian will be quite simple. It's just the disk cross the S1. It's a disk cross S1. But if you just consider the Hopf link here, it will be extremely difficult. So Clifford Tops has a construction for more than 30 pages to explain how to construct such a special Lagrangian corresponding to the Hopf link. It is very difficult. Here is the large N duality of the mathematics and physics. So the left-hand side is the Chen-Simons gauge theory. And the right-hand side is the Gromov-Witten theory. So first, so the second word is the Chen-Simons, is the mathematics, and the underlined sentence is the physics. So you can see here Chen-Simons functional is obtained here in 1974. Then Witten's Chen-Simons actually is called quantum Chen-Simons. The quantum Chen-Simons in 1989, so interpreted the Jones polynomial and predicted a lot of quantum invariants. And then here is the closed Gromov Witten. Here is a closed topological string theory. It can be the mathematical model is closed Gromov Witten, and this is the first closed large N duality. So combination of Witten and Gorbachev alpha. So the Chern-Simons of S3 is equivalent to the closed topological string theory on resolved quadrifold. This is the closed large N duality. And then this is mathematics by Recursion Formula. And this is Katz Liu. Liu is Melissa Liu at Columbia. So they give several first examples to define the open Gromov Witten. This is a part of Melissa Liu's, I think, her PhD thesis in 2001. And then Uguryev in 2000, they make the assertion for this is an open large N duality. So there's a link there. And here with the special Lagrange. But the special Lagrange is extremely difficult to obtain. So currently they have some new development in this direction. I think Shandy and some other people, they have some direction. But I'm not quite familiar with the recent progress. And here is the conjecture of Labastida-Marino-Waffa. They have a total topological open string theory free energy integer coefficient expansion, so have some BPS state interpretation. Then this conjecture interpreted from this conjecture to here, you have a new mathematical conjecture. So this conjecture here, this conjecture is purely about inside the knot theory. Then this is called the L-movie conjecture, and it's proved by Q. Liu. Okay. So then I will also skip the L-movie conjecture. It's and then also congruent scalar relation conjecture, I will also skip it. But just I want to say, so from those congruence relations, so inspired us to formulate some new volume conjectures. So here, we first look at the original volume conjectures. What about the original volume conjectures talk about? So this is the Jones polynomial, colored Jones polynomial. So colored Jones polynomial is some specialization of the colored Humphrey invariance, but because colored Humphrey invariance is two variable, colored Jones polynomial is only one variable. So you can see here the left-hand side is colored Jones polynomial, and it also can be defined by purely some combinatorial method, by cabling the knot. You can define this colored Jones polynomial. And then the right-hand side is the hyperbolic volume of the knot complements, And here I want to emphasize here, the root of unity is very sensitive. If we change the root of unity, you will get nothing. So the root of unity cannot be changed easily here. Only this root of unity works. So Jn, so what is Jn? So Jn, actually this n means n box. The Young tableau is n box. And a single box is corresponding to V2, is a fundamental representation. And then this means, Jn means the symmetrical power of fundamental representation. So the dimension of this n's symmetrical representation of V2, this is n plus 1. This is n plus 1. So that's why you evaluate the root of unity is e to the pi I over n plus 1. In some reference, they write here is Jn plus 1, Jn plus 1. And then the denominator n plus 1, you can exchange to n. There's no difference. This n plus 1 is not essential. The n plus 1 here is essential. Okay, so what's the meaning of this this volume? So Thurston actually make a very important example is the figure 8 knot. The figure 8 knot so can be obtained by those two tetrahedra. By such tetrahedra. So by such tetrahedron. So finally, this is called ideal triangulation. The Thurston's one of his most important contribution to the modern hyperbolic geometry. So for two tetrahedron, actually you have 8 vertices. 8 vertices. Then he identified 8 vertices to 1 vertices and pushed these vertices to the infinity. Here you have 12 edges, and he identified 12 edges to 2 edges. This is 1 edge. So you identified this one, and this one. So 2 edges, and this 3 edges to, yeah. So this 3 edge to 1 edge, and this 3 edge to 1 edge. So there's finally you have only 1 vertex, 2 edges, and they have 8 faces to 4 faces. And the knot, so this is, after this also identification, so you will get S3 minus K41. So this is the figure 8 knot. So this means the S3 minus a tubular neighborhood of figure 8 knot. And the figure 8 knot actually was pushed to the infinity. Then you solve the equations. You solve the equations of the Gruen equation and the completeness equation. After you solve this Gruen equation and the completeness equation, you can get the dihedral angle. Those dihedral angle of those tetrahedra. After you have the dihedral angle of those tetrahedra, then you can calculate the volume. By using the Lobachevsky function, you can calculate the volume. And then for this figure 8 knot, the volume is the volume of S3 minus K41 is about equals 2V3. Is like this number. This number. The V3 is the quotient of the hyperbolic volume and the Gromov norm. Okay, so this conjecture is currently one of the most important conjecture in low-dimensional topology because it connects two very profound areas. So one is by Jones, Whittle-Schilling-Trief, and another area is founded by Thurston. And for many years, only proven hyperbolic knot case is the figure 8 knot. This is by a Swedish mathematician, Alkeholm, and full asymptotic by Andersen. He's located at Aarhus, Denmark. And for other hyperbolic knots, people even don't know the existence of the limit. So recently, the full asymptotics of 3 twist knots was proved by Ozuki. He's a professor at RIMS of Kyoto University. And the volume part was previously proved by Kashev earlier. And by using a powerful analysis method to deal with this conjecture. So his method is a Poisson summation formula and a saddle point method. So basically, what is Poisson summation formula? So you have a, yeah. Yes, case by case. Torus knot because there's no hyperbolic volume. It's already proved by Kashev. And his collaborator, yeah. Torus knot is so simple here. Yeah, because it do not have a hyperbolic volume. And because only hyperbolic knots has hyperbolic volume. Torus knot, torus links, and a satellite knot, they don't have a hyperbolic volume. So this is pointed by Thurston. So hyperbolic knot have the most examples. A hyperbolic knot is a hyperbolic metric. You have a negative hyperbolic metric. Metrics, yes, the -1 hyperbolic matrix on the complement in S3. So in this manifold, Caspar manifold, in this Caspar manifold, you can introduce the hyperbolic metric. And by Mostow rigidity theorem, the hyperbolic volume is an invariant. Physics, so I will give a remark here. Physics was first by Sergei Gukov in this paper. Then later by Edward Witten in 2010. Another paper is analytical continuation of Chen-Simons theory. So this is two possible physics interpretation. They discuss the volume conjectures. At least in Edward Witten's paper, it's discussed the volume conjectures. Yes. That paper is very long. It's about 100 pages. Okay, so the Poisson summation formula is basically have a sigma sum. You change the sigma sum to the integration. So it's changed the sigma sum to the integration by the Fourier transformation. So this is then it's followed by the Japanese school. They solved several examples, but finally it also have some obstacle for this method because it's you need to check a lot of conditions. It's getting more and more complicated if we have more crossings. So then it's naturally stop here. So you can solve those examples. And then so by the Haber, so now I want to discussing the such volume conjectures inspired by the Haber's cyclotomic expansion. The Haber's cyclotomic expansion you can see here. This is the recursion formula. So basically you can determine H1 from J1, and from J2 H1 you can determine H2. From J3 H1 H2 you can determine H3. So H3 is an integer coefficient polynomial in Q and Q inverse. So here you see a gap. In this cyclotomic expansion, there's a gap. So n plus 1 is missing. Then you solve the gap equation. You solve the gap equation. So n plus 1. Then you will get e to the pi I. This is Q. Q equals e to the pi I over n plus 1. We solve the gap equation. This is just the root of unity we want in the volume conjecture. In the volume conjecture. And then you see here, if in this equation, in J and K, if we evaluate as this root of unity, what happened? Because here's n plus 2 here, n plus 2. This you just get a 1. Huge difference. The root of unity, if you change to another root of unity, it just give you 1. It's not. It's just a very small number. But if you as this root of unity, it will become exponentially large, and you have the volume conjecture. This is just the root of unity for the volume conjecture. So it's like when you have the cyclotomic expansion. If you evaluate at n plus 3, and this all disappear, it just have finite term remained. So if you have only finite term remained, when n goes to infinity, you still have finite term. It cannot give you exponentially large term, right? So this is like a necessary condition. But finally, it's also sufficient condition. In the volume conjecture, it tells you also sufficient condition. And just to give you the volume. And then we use this idea to study the colored SUN invariants. Then we have such expansion. So colored Jones polynomial is like a colored SU2 invariance. And then we generalize from SU2 to SUN. Then we make the following conjecture. And we will find that this gap expand. I will wonder whether all the roots of unity in this gap can be used for the volume conjecture. So the answer is yes. So we also solve this gap equation. And then we found that all those stuff in this gap can be served as the volume conjecture. So this is our volume conjecture for colored SUN invariants. So this is also exponentially large and give you the volume. And then we can prove this is also true for this figure 8 knot. Also true for the figure 8. So here you can see, if the colored Jones polynomial just n equals 2, you just A can be only 1, right? There's only one choice. A only can be 1. And this is original volume conjecture for n plus 1. But for colored SUN invariant, A can be from 1 to n minus 1. If we study colored SU5, A can be 1, 2, 3, 4. We have 4 different choices of the volume conjecture. You fix n. SUN, small n, you fix small n. Yeah, it doesn't depend. Just they all give you the volume, but sometimes for some root of unity it converges fast. Some some root of unity converge a little bit slow. All give you volume. And here, because today I don't have time for I only have like 15 minutes left. Yeah, 15 minutes left. So I should. No, because I start late. I start late. The super polynomial, I don't have time. So super polynomial in the sense of downfield Gukov and Rasmussen. And so I also discovered the volume conjectures. So I can send you the slides if you have interest. So this is also connected to the smooth forward genus. It's also another very interesting phenomenon. So I don't have time. So I just skip this part. I tell you, so there's also volume conjectures for super polynomials for the categorification version. But today I don't have time. I removed this part. So to the last part for the volume conjecture of Recursion Triumph and Triumph Zero invariance. So this is part of my work with Tianyang. So we consider so here's the QS. So I said so this is the comparison of two different notations, physics notation and our notation. So original root of unity. This is original root of unity. In our notation is Q1. It's just this one. And we want to consider the root of unity here. So actually, Recursion Triumph, they defined the root of unity at Q1, Q3, Q5. And this French school, Blanche, Haberger, Masbaum, Vogel, they again extended them to Q4K plus 2. So we propose our volume conjecture at Q2. For this closed orientable manifold, so this is complex manifold. Complex volume is defined by Thurston, is the volume part and the Chen-Simons part. And here is the ambiguity of the Chen-Simons part. So if you want to take the absolute value here for the Recursion Triumph invariance, you can just approach the volume. And you can remove this ambiguity and remove this Chen-Simons part if you take the absolute value here. So this is our new volume conjectures at Q2. And here the denominator is not essential. You can change to Q, you can change to R. We use R minus 2 just want to get a beautiful graph. So R minus 2 actually is the level of the representation. So 2 is the rank, and R is the level plus rank. So R minus 2 is the level. So that's why we get a beautiful graph. And R is odd, because here R and S should be co-prime. We study Q2, R should be odd. And this is the volume conjecture. And then we study some, in our original paper, we made some numerical calculation. Finally, those example has been proved by Ozuki, also by using his method, Poisson summation formula and the saddle point method. So MP denotes the P surgery, Dyson surgery of K in S3. So Recursion Triumph invariance is given by the following identity. So this is our older friend, is Curtis-Jones polynomial, is our older friend. Here is some summation. So from n equals 2 to r minus 2. So all the summation. This is some quantum integer, the numerical part of the quantum integer. So in order to verify the volume conjecture, it's equivalent to calculate the following identity. So we studied the quotient of the adjacent terms. So here, MP is hyperbolic when P is, absolute value of P is greater than 4. So here, the knot K is the figure 8 knot, is a figure 8 knot. So like a P equals 5, 6, 7, or it's a hyperbolic manifold. And this example has been proved by Ozuki. So here is this is the table is calculated by me and Tianyang in our original paper. So this is SNIPE, you can, from the program SNIPE, you can get the hyperbolic volume here and the Chen-Simons term. So you can see here, when R is 501 is odd number, so it's very close to the volume, the approach to the volume. So this is our numerical calculation. Finally, it's proved by Ozuki. And this Q order, we don't have time for this one. So Q order is, and then this is the first version of our paper. So we first discovered the volume conjecture from the Triumph-Villot invariance. So Triumph-Villot invariance was originally defined for closed 3 manifold. And it became a TKFT for 3-manifold with non-empty boundary. Because you take with a boundary, you will have a vector space on the boundary. And here we just do a small modification. We use the Thurston's ideal triangulation instead of the usual triangulation in the construction. Then we obtain a real valued number instead of a TKFT with non-empty boundary, like a Caspar manifold and a totally geodesic boundary. Totally geodesic boundary stands for the boundary can be a high genus surface, like genus 2, genus 3. And for Caspar manifold, the boundary can be a torus boundary or can be Klein-Bottle boundary. So for any hyperbolic 3-manifold with Caspar or totally geodesic boundary and run over all the numbers, we have the volume conjecture. We have such a volume conjecture. And here, I want a comparison of the volume conjecture with the original volume conjecture. So original volume conjecture is proposed for such examples. So you can see here, the S is the complement of hyperbolic knots and the links. So for when you use 8 tetrahedra, there's only 299 examples. But now we propose the volume conjecture for all those examples. Even there's a line for the totally geodesic boundary, like G, the high genus boundary here. Nobody calculated how many examples. So this 299 example was included in such examples. I will make the numerical calculation for those examples. This torus boundary and this is Klein-Bottle boundary. So here is the Gisaki manifold. It's non-orientable manifold, Gisaki manifold. This means Gisaki manifold, you have only one tetrahedra. You identified all the 6 edges to one edge. Here, this is the place for the figurative knot. Figurative knot is here. This is figurative knot. You use 2 tetrahedra, right? 2 tetrahedra. And it's a sister. And 3 twist knot. 3 twist knot 5-2 is located here. Located here. So our volume conjecture for trivial zero type invariance was proposed for all Caspar manifold, the most of which are knots and links complements. So the volume conjecture only proposed for such examples, and then we propose for all the examples, hyperbolic manifolds. And this is also some numerical examples for the Gisaki manifold. So this is a non-orientable Caspar manifold. So I tell you, so Gisaki manifold, Gisaki is a German mathematician. So he identified the 6 edge to one edge, just to one edge, 6 edge to one edge. So so the boundary is a Klein-Bottle. And so this is the quantum Shakespeare symbol. The quantum Shakespeare symbol actually is a complicated stuff. It looks like an innocent rabbit here, but it's like a monster. If you want to expand all the terms, it's quite complicated. So I don't want to expand here, just let it look like an innocent rabbit. So consists of integers such that, so it's run over all these integers. And this is the quantum Shakespeare symbol. So this is the Gisaki manifold. So quantum Shakespeare symbol is the building blocks for trivial zero invariance. And we calculated those examples. You see here, we call the name the quantum volume. So also 501, so it approaches the volume. This is V3. So Gisaki manifold is just a V3, not a 2V3. The figurative knot volume is a V3. So why we called such invariant of quantum volume? And I want to emphasize this example haven't been proved yet. Why called quantum volume? So we witness very drastic and huge cancellation for the figurative knot complements. Some amounts of trivial invariance even reach like 10 to the 500. So while the final invariance is just around 10 to 140. So the original volume conjecture is like you adding up some numbers and to become a very large number, like this one. But here is like you already have like a lot of big monsters. They fight each other. Then finally, there's a middle-sized monster is remained. Because all the big-sized monsters, they have cancelled out. Positive, negative, they cancel out. So this is the major difference between our volume conjecture and with the original volume conjecture. So it becomes more difficult to prove. More difficult to prove. Okay, so then I want to introduce some recent developments of these volume conjectures. So Ozuki first refined our volume conjecture of rotating triumph invariance at Q2 to full asymptotic expansion. Then physics flavor is by Gandomi, Romo, and Yamazaki at IPMU. And proved the case of closed hyperbolic three manifold obtained by integral surgery along the figurative knot. So Ozuki proved infinite examples of a series of examples of closed manifold of rotating triumph invariance. And Ozuki Takata further recognized the secondary term in asymptotic expansion of the random mass torsion. So in Witten's asymptotic expansion, the random mass torsion is the primary term because they consider the first root of unity. Then we consider the second root of unity, it became the secondary term because the volume became the primary term. Then Detcher, Kafjani, Yang, they proved the volume conjecture of the complements of figurative knot and the Borromean ring. They use some special technique to prove that. Prove this example. And then Detcher, Kafjani, again, they established a relation between the trivial invariance at Q2 and the Gromov norm of three manifold. And then they obtained the lower bound for Gromov norm for any compact oriented three manifold with empty and toroidal boundary. And then Kafjani, she told me at ETH when she visited me for a conference last year. And she said that this result was praised by Clifford Tops. It seems an important result, this result. Because when they post the paper on the archive, and Clifford Tops wrote them an email to congratulate them on this result. It seems an important result. I'm not very familiar with this area, so I just tell you this. Then this is some this also proves some non-volume case. This do not norm zero case. Yeah, it's 3 minutes. Okay. Because I started later. Okay. And then Detcher, Kafjani first related the Anderson-Nussbaum-Ueno conjecture to the growth of the trivial invariance of the hyperbolic manifold at Q2. Then they proved that our conjecture can imply AMU conjecture. This is some conjecture in the dynamical system. Then as integrality, this is our minor conjecture. It's in our paper. I do not introduce today. And the recent paper is by Yang. They proved some fundamental shadow link. And this is the Hong Kong school. They proved, they obtained a full asymptotic expansion. And this is my new result with Jun Murakami. We consider the general case. So we studied the quantum 6 symbol, and we obtained this is dominated by volume and the Gram matrix of a single tetrahedron. And we also find a new conjecture. The new conjecture can explain the big cancellation. So I tell you some bigger monsters, they have canceled out. So this is a symmetric conjecture explaining the very mysterious bigger cancellation. And this is maybe have some hidden nature of the, uncovered hidden nature of the quantum 6 symbols. And the Zhenghan Wang, he's a professor at Microsoft Q Station and UC Santa Barbara. So he pointed out that it's puzzling how the non-unitary case can arise from the unitary 3D quantum gravity. So this is, so he in the paper he writes, so our volume conjecture should corresponding to a non-unitary fixed theory. And Rashetikhin in early of this year, he also put a paper on the archive that said, so this is at a Q2 and other root of unity, it is non-unitary. So I quickly, the last summary. This is the Color-Jones polynomial, superpolynomial, and Hanfly PT polynomial. And the Q1 and Q2, they're almost the same. This is original volume conjecture, original style. And this is a 3-manifold invariance, Rashetikhin trivial and a quantum 6 symbol. And the Q1, they don't have the volume conjecture. It's polynomial growth. This is Witten's asymptotic expansion conjecture. And it's polynomial growth. And this is also similar, should be called polynomial growth. And the Woodward conjecture is also polynomial growth. And at Q2, we discovered the volume conjecture. It's exponential growth, and the growth rate is proportional to the volume. So the volume conjecture only happens here. So previously, the people think Q1 and the other root of unity should be similar. They should be by some Galois transformation. Now, the huge difference has been revealed. And the more interestingly, so it should be corresponding to the non-unitary fixed theory. This has confirmed by some top mathematical physicist. Because the reason is that the quantum integer became negative. So, thank you.